Here in 7.7 we'll be looking at some techniques for approximating integrals. And to start, we'll revisit some Riemann sums, in other words using rectangles to approximate the area, where what we call a left Riemann sum will be summing up rectangles using the left endpoint of each rectangle to determine the height of the rectangle. So you remember the way that we'll construct the Riemann sum is we'll take the interval from a to b, so those would be in this case starting at x0, which is what we're going to call a, and the right endpoint in this case would be x4, because here we have 4 subintervals. So here we're using n equals 4. Call that b. So this would be a way of approximating the integral from a to b. So ln in this case would be L4 if we're doing 4 subintervals. But let's think about how this formula would be in general. So in this case, the width of each rectangle is delta x, and it would be given by the length of the interval, b minus a, divided by n. Okay, so that gives us n equally spaced subintervals. To get x0, the left endpoint, that would always occur at a, and then we add delta x to get to x1, the next subinterval, and so on. And we're going to be using the left endpoint of each of those subintervals to determine the height. So in this case, it would be delta x, our width, and then using the height at x0 is f of x0, f of x1, and so on. In this case, we wouldn't go all the way to the right endpoint. We would stop in this case at x3, or in general, we would stop at f of x n minus 1. Okay, so we wouldn't go all the way to the last endpoint here because the last subinterval uses the left endpoint. On the other hand, if we're doing the right Riemann sum, we're going to be using the right endpoint on each subinterval to determine the height of the rectangle. So we would have delta x, f of x1 would be the first right endpoint of that first subinterval, f of x2, and so on, all the way out to the last subinterval here. The last subinterval has the right endpoint at xn, which would be our b, right? Okay, so this is just a reminder of how to do this for left and right Riemann sums. Okay, after we've partitioned the interval a to b into the subintervals, then we evaluate the function at each left endpoint if we're doing the left Riemann sum, or at each right endpoint if we're doing the right Riemann sum, summing up all those function values, and then multiplying by the width, delta x. Okay, so that gives us an approximation under the curve. As you can kind of visualize here with these pictures, it's not going to be an exact area, but it'll be a reasonable approximation. We see that because there are these gaps in between the curve and the rectangles, there is some error involved in this approximation. So one way to kind of correct the error a little bit is, instead of using left or right Riemann sums, we can try a different technique. And here we can look at using midpoints. Notice that in this case the error appears to be a lot smaller because for each rectangle, there's part of the rectangle will be above the curve, which is over approximating, but another part of the rectangle will be under the curve, which is under approximating, and so that tends to balance out a little better. In other words, there isn't going to be a big over or under approximation, because it's a little bit of both in each of them that tends to balance out. Okay, but instead of now using the left or the right endpoint, we're going to need to find the midpoint of each of these subintervals. Okay, so in this case we would take the same delta x, take the length of our subinterval, which in this case would be from b to a, or sorry, from a to b. So you would do b minus a over n to get our delta x. And then we would multiply that by the height of each of these rectangles, which is given by f of x1 bar, f of x2 bar, so on, all the way out to f of xn bar. Okay, where the bar indicates that we're taking the midpoint of the subinterval. So here, x1 bar, for instance, would be the midpoint between x0 and x1. So it would be taking the sum of x0 and x1 and then dividing by 2. Or x2 would be, x2 bar would be the midpoint between x1 and x2. So you find the midpoint by adding the endpoints, dividing by 2, and so on, right? So if I were to do just a random xi bar, this would be the midpoint between xi minus 1 and xi. Okay. And so there, the midpoint formula appears to be a much better approximation than doing a left or a right Riemann sum. And then one more rule that might also be a better approximation than the left or the right Riemann sum would be the trapezoidal rule, which instead of using rectangles is now using trapezoids. So as we can see here, to find the area of each of these trapezoids, we're not using a rectangle formula, instead we're using a trapezoid formula. So say I'm looking at just this first trapezoid, which has a shape like this. So it's got two bases. One base over here has a height of f of x1, and the other base over here has a height of f of x0. And the width at the bottom would be delta x. So the area of this we'll call it the ith, or actually this would be the first one, right? So the area of this first trapezoid would be taking delta x, right, the width, times the sum of f of x0 and f of x1, the sum of the two bases, and then dividing by 2. So that's just using the area of a trapezoid formula, right? Or here, if I were to find the area of the second trapezoid, here, A2 would have same kind of formula, delta x over 2. So you can imagine it's the same width, but the bases are now f of x1 and f of x2. So f of x1 plus f of x2 and then divided by 2. So so in general, what is it if I want to find, say, just some random one in the middle, say AI, the ith trapezoid, delta x over 2, f of xi minus 1 plus f of xi, where, yeah, that would be the ith trapezoid. So to get the sum of all these trapezoids, we can add them up. You can imagine that summing up all these trapezoids, A1 plus A2 and so on, all the way out to the nth one. Say the last one was AN. Well, then you'd have each of these summed up here. So they each have a delta x over 2. Okay. So I start with f of x0 plus, then I'm going to have f of x1, but in the next one, notice that f of x1 occurs again. So there's actually 2 f of x1. There's going to be f of x2 twice as well, because f of x2 will be in A2 and also in A3. so on. So all the ones on the middle here are going to have a coefficient of 2 in front. All the way out to the nth one here. So here n minus 1, and then the last one here, f of x n, will not have a coefficient of 2, because here f of the last one, if this were the nth one here, say an, we do an here, be f of x n minus 1 plus f of x n, but here f of x n would be the only one. F of x n minus 1 would be combined with the one that came in the rectangle before, or in the trapezoid before. Anyway, so here is our trapezoidal rule. Right, it's delta x over 2, f of x0, and then all the ones in the middle will have a coefficient of 2. So 2f of x1 and so on, out to 2f of x n minus 1, and then the last one, f of x n, has no coefficient of 2. Okay, so let's try an example here. Suppose I want to use the trapezoidal rule and the midpoint rule with n equals 5 subintervals to approximate the integral from 1 to 2 of 1 over x. Okay, so let's start by picturing here the interval. So we're going from 1 to 2, and we're using n equals 5 subintervals. So we imagine here we're going to break it into 5 subintervals. Okay, so what's the width of each of our subintervals? So delta x in this case would be 2 minus 1 over 5, which is 1 over 5, or 0.2. So now let's find all the grid points in between here. Okay, so the left endpoint is 1, so add delta x to get to the next grid point, which would be 1.2. And then add delta x again to get the next grid point, which would be 1.4. And then the next one would be 1.6, 1.8, and then the final one is 2. Okay, so those would be all the points in between. So that's like our x0 is at 1, x1 is 1.2, x2 is 1.4, and so on. And then xn, or in this case x5, would be 2. Okay, so let's start with the trapezoidal rule. So here we're going to do T5. So let's kind of write out what the rule was. It was delta x over 2. And then we'll do f of x0, which is 1, plus f of x, 2 times f of x1, which is 1.2. 2 times f of x2, which is 1.4. 2 times f of x3, which is 1.6. 2 times f of x4, which is 1.8, and then just f of x5, which is just f of 2. Okay, so notice the first and the last one did not have a coefficient of 2, but all the ones in between did. Okay, so now we can put each of these values into the sum. Delta x was 0.2 over 2. F of 1 would just be 1 over 1. 2 times 1 over 1.2. 2 times 1 over 1.4. And so on. 2 times 1 over 1.6. 2 times 1 over 1.8. And 1 over 2. Okay. So now it's in a form where we can just now evaluate it in our calculator to get an approximate value. So after approximating in my calculator, I get a value of around 0.6956349,206. Okay, so I just kind of wrote down all the decimals that my calculator gave me. So this would be the approximation that we get from doing T5 the trapezoidal rule with 5 subintervals. Let's see how we would do the midpoint rule now. So that's M5. So in this case, we'll remember be doing delta x times. Now, before I write out the rest, we need to actually find the midpoint. So using the grid that we wrote up here, let's fill in now the values at each of the midpoints. So we're going to go through and find the midpoint of each of these subintervals. So like the first midpoint here would be x1 bar, which you can find would just be adding 1 plus 1.2 and then dividing by 2, or here you can maybe do it mentally and you get a midpoint of 1.1, right? Did the same thing here, 1.2 to 1.4, so the midpoint would be 1.3. Between 1.4 and 1.6, the midpoint is 1.5. Between 1.6 and 1.8, the midpoint is 1.7, and then the last midpoint here would be 1.9. Okay. So those would be the values that we're going to use for the midpoint rule. So it's just f of 1.1, f of 1.3, f of 1.5, f of 1.7, and f of 1.9. Okay. And in this case, let's write out what that would be. So delta x was 0.2, 1 over 1.1, 1 over 1.3, 1 over 1.5, etc. Okay, so now it's ready to evaluate this in my calculator. And let's see what we get when we do that. Okay, so after evaluating this in my calculator, my approximate value is about 0.6919078857. Okay. Notice it's a little bit different than the other approximation. So the question is, okay, which one of these is a better approximation? So if you had to guess, and you were to look at the pictures from the previous slides to sort of demonstrate how these two approximations work, which would you guess is a better approximation? So take a guess, and then we'll find out in the next video what is actually a better approximation.